All right, welcome back to our series on designing a computer from scratch. We're calling this section Appendix A2 because it's beyond the initial design. And what we're going to do in this section is add support for subroutines. Let's add a set of instructions to jump to subroutine and return from subroutine instruction. Call the mnemonic JSR and the mnemonic RTS. We're going to add it into the table of opcodes at A for JSR and B for RTS. For JSR, it has the same format as a jump or a branch. It stores the address that you're going to jump to. And RTS has no parameters, just the 4-bit opcode, and that's it. In the design up until this point, there's been no subroutine support. Everything would be called inline or with branches if equal, that sort of thing. Yeah, but a larger example can leverage subroutines. If you're doing something repeatedly, it can get a big advantage over it. The way we would implement a subroutine is to store the next address +1 when a JSR instruction is encountered, and we'll store it in a signal wire called wreturn address. And when we do the RTS return from subroutine, it'll pull that and use that as the next address for the PC. We need to add some signals. We'll add the return address. It's a 12-bit value. We'll also have to create a load address value to load the program counter with. Up until now, we've only loaded it with the bottom 12 bits of the instruction, but we will need to load it with return address, which is not the bottom 12 bits of the instruction, it's the current PC +1. We also need to add the two instructions, the two op signals for the JSR and the RTS. We will need to create the decode for that as well. Opjsr is 1 when the opcode bits are 1010 and RTS when they're 1011. That goes in line with all the rest of the decodes. And let's write a little process that stores the program counter +1 into wreturn address when a JSR is encountered and at that gray code value of 2. Very similar to a lot of the other code we've already written up to this point. It just stores the return address. So we'll add a mux to the PC load value. Up until now, the PC load value has only been loaded with the ROM data, the bottom 12 bits, and it was connected directly up to the entity map. In this case, we'll create a signal wload adder that will be a multiplexer that will select either that ROM data for most cases, or if it's an RTS, it'll select that return address that we've created. The program counter change to do that is here. It shows the PC load adder address value being set or mapped to load the PC. When an RTS is encountered or for any of the jumps, it sort of prepares it and has it ready to load. We have to tweak the wloadpc to add the RTS and JSR. It will always load if it's a jump. It'll always load if it's a RTS or JSR. It's always a flow control change in all three of those cases. And of course, the conditional branch is only flow control change is if the Z bit matches the condition. Our test code is going to be fairly simple. We will jump to, first line will be a JSR to label 1, and it'll execute a no op, and then it should do an RTS, which should return to the next address, and then it'll do a jump back to start. So that did compile correctly. The assembler supports these two instructions. And that would mean we would expect to see a step from 000 to 003 to 004 to 001 to 2 to 0. If the PC goes from 0 to 1 directly, then the JSR failed. So if we're here and we go here, then that jump subroutine didn't happen. If the PC goes from 4 to 5 directly, then the RTS failed. So if we go from here to here, if we ever go to here, if we go from here to here, then we know that the RTS failed. So that'll be our test conditions. We expect to see this pattern, and if we see these other two patterns, it's a failure. And it worked. We see the 0 to 3 to 4 to 1 to 2 back to 0. So we were able to execute the subroutine and run it and return and not go to places we weren't supposed to go and go to the places we were supposed to go. Wasn't too hard of a change, a little bit of debugging to get to this point, but that's basically how it works. So what do? We added a single level subroutine facility, added a JSR and RTS instruction. We tested and it works. It does not support nested subroutine calls. You can't call a subroutine from within a subroutine. They can only be a single level, but you can have obviously as many subroutines as you want. You just can't call one subroutine from inside of another subroutine. For a larger code example I got about 75% reduction in code size. Depends upon how repetitive the functions are. If you're running to a lot of address ports and those ports do the same function but you have multiple copies of them, it might get this kind of a number for reduction, or it might be just a few percent. One thing for sure we know is that the penalty is a slower execution time because the JSR and RTS instructions will take time. So I created a branch and checked it in, and it's the CPU appendix 2, CPU 001 APB2. As usual, the design of CPU entity is up in GitHub if you want to check out the tip, the current version, and the top level entity stays the same. Thanks for watching. If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well. We have a store in Tindy where we sell all of our cards. Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.